Welcome to dear students. Today in this video, we'll discuss about the ideal diode equation of PN junction. What is meant by ideal diode? Ideal diode, a diode that like as a perfect conductor when voltage is applied in forward bias and like as a perfect insulator when voltage is applied in reverse bias. So when positive voltage is applied across the anode to cathode, the diode conducts current at all instantly, and we apply the voltage in reverse direction, the diode currents not conducts at all. So let's start the complete derivation of ideal diode equation. First we apply the forward potential Vf to the unbiased diode, then the potential barrier of diode will be lowered by amount of energy EVF. This topic or this term we already discussed in energy band picture of PN junction. Means when we apply the positive potential, the potential barrier which will be reduced. That is, its energy will be EVF. Then the majority of charge carriers crossing the junction means electrons and holes are crossing the junction, and the diffusion current density will be increased by factor exponential EVF upon kT. This EVF upon kT means the Boltzmann factor, and the diffusion current density will be increased. Diffusion current density means the diffusion current per unit cross sectional area of that semiconductor. But what is meant by diffusion current? We know that in semiconductor material there are two types of current. First is drift current and second is diffusion current. Drift current is the when the semiconductor material number of electrons in random motion, we apply some electric field, the electrons movement in particular direction, that velocity of that electrons is called as drift velocity, and this movement of electrons of charge carriers means the drift current. And diffusion current means if the number of electrons and holes is higher or greater in one part of region of semiconductor material as compared to the another part of that semiconductor material, then we can say that the concentration gradient exists in the material. So the tendency of higher concentration means greater region of the electrons and holes moving to the lower concentration of electrons and holes. This movement causing the current is called as the diffusion current. Means when we apply the positive potential, the diffusion current density component, this J star HP and J star En, the star denotes means forward bias, and only just we denote the J's means in unbiased. The J star HP means diffusion current density of holes of P region in forward bias equal to JHP means diffusion current density of holes in P region in unbiased to exponential EVF upon KT equal to JHN. We write JHP equal to JHN because in unbiased the Fermi energy level in middle of the both bands means conduction band and valence band, then means the holes in P region and holes in N regions are equal concentration. Therefore, we'll write equal. Same in equation second, we'll write J star En means diffusion current density of electrons in forward bias of N region equal to JEN diffusion current density in unbiased of electrons in N region equal to exponential EV upon KT equal to JEP. This quantity also equals because electron concentration in N region and P region in unbiased are equal. Therefore, next, the drip current density components have not changed and have the same magnitude as in equilibrium case. In forward bias, drip current will not change. Therefore, diffusion current density components are not changed. Then, the hold current density across the forward bias junction is JH. Forward, this is the net hole current density. Net hole current density means diffusion current density, whole diffusion current density in forward bias minus in unbiased. We put the equation first in this equation, J star HP value of equation first we put, we'll get this equation, that is This is equation third. Similarly, we can write the net electron current density across the forward bias junction is means Je is equal to J star En minus JEN. J star En denotes the diffusion current density in forward bias of electron minus diffusion current density of electron in unbiased. We put equation second means this value. We get this equation. Now next, the total current density across the forward bias junction is sum of electron and hole current density components means equation sum of equation third and fourth. That is the total current density across the forward bias. In we note that in this equation we know put the values of the drip current because drip current is not change, only change of a diffusion current. Therefore we'll put the all the quantities of diffusion current density in this equation. Therefore the total current density across the forward bias junction is the sum of the electron and hole current density components mean equation third and fourth, that is JH plus JE. We put these two values, then we write some common terms JHN minus JEN. This term will be denoted by J naught. J naught, and this equation will be J equal to J naught into exponential EBF upon KT minus 1. Then next, but current density, we know that current density J equal to current per unit area, that is I upon A. We put this value J equal to means we put J upon A equal to I. The in this above equation, that is this equation J naught, this equation J equal to J naught exponentially V upon KT minus 1. We put the I upon A, J upon A equal to I. We get the equation means this equation written as I equal to I naught into exponential EVF upon KT minus 1. This above equation I equal to I naught upon into exponential EVF upon KT minus 1. This equation is known as a ideal diode equation where Vf is the forward bias voltage. We apply the forward bias voltage, and in reverse bias it will be replaced only just by minus Vf is equal to minus Vr and denotes the reverse saturation current. Minus I will be denotes the reverse saturation current. So I hope we have to have better understand this ideal diode equation in this video. Thank you, thank you, thank you.